So we'd like to look at what's called factoring polynomials, factoring algebraic expressions. This is section 1.5. Before we actually begin factoring algebraic expressions or polynomials, we want to kind of review factoring whole numbers into primes. So what's a prime number? What is a prime number? So I remember doing this like back in 3rd grade. A prime number it's a whole number bigger than 1 is a whole number greater than 1. That's the symbol for the greater than. So it's a whole number greater than 1 whose only divisors are 1 in itself, whose only divisors are 1 in itself. So it's only divisible by 1 in itself. So examples of primes. Well, first of all, 1 is not a prime. 1 is not a prime. It has to be a number. Primes are always bigger than 1. So the first thing you have to check is 2. Is 2 a prime? Yes, 2 is a prime because the only thing that 2 is divisible by is 1 and 2 itself. How about 3? Yeah, 3 is a prime, right? The only thing that 3 is divisible by 1 and 3 itself. How about 4? Is 4 a prime? No. 4 is divisible by something besides 1 and 4, right? It's divisible by 2, so we exclude 4. 5. 5 is a prime because the only numbers that divide 5 are 1 and 5 itself. How about 6? No, 6 is not prime, right? It's divisible by 2, also it's divisible by 3. Other primes include 7, 11, 13, 17, 19, 23, 29, 31, and so on. There are actually infinitely many prime numbers. But those are some of the smaller prime numbers. So I remember back when I was in 3rd grade that we would be asked to factor whole numbers into primes. Let's see if we can do some of that. Let's just do some examples. Just kind of a review. It's not super useful for this section. It's really not useful for this section at all. It's going to be useful later in some later sections. But right now I just want to kind of review the concept of what is factoring. So I'm going to ask us to factor the whole number into its prime components. All right, let's say we got the number, 100. I'm going to write down 100. I'm going to make what's called a factor tree. Now, 100 is not prime, right? You can break 100 down into what? 10 times 10. So I'm making a little branch here and a little branch here, saying 10 times 10 is 100. Now, is 10 prime? No, 10 is not prime, right? You can break that down into what? Making branches there, 2 times 5. And the other 10 I can break down into 2 times 5. Now the question is, are 2 and 5 prime? Yeah, 2 is a prime, right? Only thing that divides 2 is 1 and 2. 5 is a prime because the only thing that divides 5 is 1 and 5. And then 2 here's prime and 5 here's prime. So I'm circling all my primes. So notice that we have 2 copies of 2. So that's what? 2 times 2. And we have what? 2 copies of 5. 5 times 5. So how do we call these 2 2's? These 2 2's here. We call that 2 squared, right? 2 times 2 is the same thing as 2 squared, 2 to the 2nd power. How about 5 times 5 here? 5 times 5, I'm underlining in green, underbracing in green. 5 times 5, using algebra notation, we write that as 5 to the second power. So here you have it. This is your prime power factorization. Prime power factorization of 100. So that's the way you write 100 in prime power factorization. 2 squared times 5 squared. So you have 2 copies of 2 and 2 copies of 5 that make up 100. So these are the prime numbers are the building blocks of all other whole numbers. All right, let's just do another quick example so we have the hang of this. What do I want to do here? How about I got the number 360? It's a nice number, right? 360. I'm going to write that down on the side. I'm going to make a factor tree. Tough to come up with numbers. Well, we know 360 is even, right? 360 is even because it ends with a 0. 0 is an even digit. So anytime you have a number that ends with an even digit, it's an even. So I can say, okay, it's even, so it's divisible by 2. So I can put 2 here as one of my factors. I can do what? 360 divided by 2 to find out the other factor. That would be 180, right? Okay, so 180 times 2 makes 360. Now here 2 we know is prime, right? The only thing that divides 2 is 1 into itself. How about 180? 180 prime? No, it's even, right? Even numbers that are bigger than 2 are never going to be prime, right? So it ends with a 0 there on the end. It's definitely even, so we're going to have 2 times something to give us 180. 2 times what? 2 times 90, right? 2 times 90. Now, 2 is a prime. I'm going to circle that. How about 90? Is 90 prime? No, it's an even number that's bigger than 2. We know 2 times something gives you 90. Let's see, 2 times what? 45, right? 2 times 45 gives you 90. We're going to circle 2 because it's prime. How about 45? Is 45 prime? Actually, 45 is not prime, right? We know 5 times 9 gives us 45. Now, we know 5 is a prime, right? The only things that divide 5 are 1 and 5. How about 9? Is 9 prime? No, 9 breaks down into what? 3 times 3. See if I can scroll this a little. There we go. 3 times 3. Now, 3 is prime and 3 is prime. So, okay, we got all the primes now. We got what? 1, 2, 3 copies of 2. 1 copy of, well, let me erase that. 1 copy of 5. And we have 2 copies of 3. So I'm going to put them in the increasing order from the smallest prime to the largest prime. So I'm going to have what? 2 times 2 times 2. Those are the 2's. Then we have the 3's. We have 3 times 3. And then we have times 5. We just have 1 5. All right, so how about these 2's here? We can call that 2 times 2 times 2. That's going to be 2 cubed, right? 2 cubed. 2 to the third power. Times 3 times 3. What do we call 3 times 3? We call that 3 squared. And what do we call just 5? That's just 5 times 5. There you have it. Here is the prime power factorization of 360. It's 2 cubed times 3 squared times 5. So basically what we're learning to do here, we're learning to take whole numbers and break them up into their more basic building blocks. So the idea is we want to be able to do this with algebraic expressions. We want to take algebraic expressions, polynomials, and break them up into their more basic building blocks.